Imagine you're a designer, maybe a student, or maybe you're just really curious about the digital world, and you're looking at this intricate FPGA chip. Pretty amazing piece of tech, right? But then that big question hits. How do you actually program this thing? The software tools, these tool chains, they're kind of the unsung heroes. Or, let's be real, sometimes they're the biggest headaches you'll face. So today we're doing a crucial deep dive into this complex world of FPGA development tool chains. And look, this isn't just about picking some software. No, it's a strategic choice. It affects, well, everything: how fast your project moves, how productive your team is. We've gone through a whole stack of sources, detailed comparisons, lots of community feedback, you name it, basically to give you the shortcut to being really well informed on this.
Yeah, and what's fascinating, what really comes through from the sources is just how segmented this market is. Each tool chain, it's really optimized for specific jobs, specific kinds of users. There's no single best tool here. So our mission today is to break down four of the big ones: AMD Vivado, Intel Quartus Prime, Microchip Libero Seiko, and Lattice Radiant. We want to get past the marketing fluff and look at their real strengths, their weaknesses, sometimes pretty frustrating ones, and how they actually work. We'll show you why choosing a toolchain isn't just software. It's kind of like signing up for a whole development philosophy, complete with its own set of trade-offs.
Okay, let's jump right in then. First up, AMD Vivado. The sources definitely paint this one as the high-performance titan of the group.
That's a good way to put it. Vivado is squarely aimed at high-performance, high-density computing. Think complex designs, AMD's top-tier stuff like Versal, Ultrascale plus Late. You see it a lot in data centers, AI, really demanding compute tasks.
Right. And what gives it that titan status? What are the key strengths that make it stand out for those heavy-duty jobs?
Well, a huge piece of the puzzle is the Vitis platform. This is AMD's really big push to sort of democratize FPGA development. It shifts the focus from pure hardware design towards something more software-centric. Vitis brings in high-level synthesis, HLS. That means you can actually generate hardware logic from C or C++ code, which is, a massive deal for software engineers.
Okay, HLS. So that lowers the barrier significantly for people who maybe don't live and breathe Verilog or VHDL.
Exactly. It lets software teams tap into FPGA power without needing super deep RTL expertise. And Vitis includes specialized tools, too, like Vitis AI for machine learning, Vitis Model Composer for algorithms. It's all pretty tightly knit together.
That really does sound like a potential game changer, giving software folks more direct access to the hardware's potential. Is it living up to that promise, you think?
In many ways, yes, especially for the right kinds of applications. But beyond HLS, Vivado just has some really advanced features for complex designs, things like dynamic function exchange or DFS.
VFX, what's that about?
It lets you reconfigure parts of the FPGA fabric while it's running. Imagine updating a processing block, maybe swapping an algorithm, without a full system reboot.
Whoa, okay. That's powerful for like power saving or even field updates.
Precisely. Reducing power, size, enabling system upgrades on the fly. Combine that with incremental compile and abstract shell tech, and you can iterate much faster on big designs, only recompiling what changed.
A lifesaver on huge projects, I bet.
Absolutely. And for hitting those tough timing goals, max clock speed, Fmac X, Vivado has advanced tools like report QRR assessment, intelligent design runs, plus integrated chip scope for robust on-chip debugging, lets you see what's really happening inside.
So incredibly powerful, built for the really tough stuff. But power often comes with complexity, maybe some frustration. And here's where it gets really interesting for me. Reading the feedback, you've got all the sophistication, but the user experience doesn't always match up. This solid core flawed shell idea seems to really fit Vivado based on what people say. What are those quirks?
Yeah, that description fits. Vivado's power definitely demands resources. People often call it huge, incredibly complex, resource-hungry, sometimes very slow, a big place in route run. It can eat 30, even 50 gigabytes of system memory.
50 gigs. Okay, so not your average laptop software.
Not at all. Even the installer used to be enormous, though they've improved that a bit. And naturally, with so many features, the learning curve is steep. It's just considered much more complicated than some others. Oh, and the license. The full enterprise license is a serious budget line item. There is a free ML standard version, but it's limited to certain lower-end devices.
And the GUI. That seems to be a common pain point in the comments we saw.
The GUI. Often called counterintuitive and, frankly, prone to weird, frequent crashes. During synthesis, simulation, getting stuck, needing a forced quit, it drives people nuts.
So annoying when you're on a deadline.
Exactly. which is why many experienced users just ditch the GUI for critical stuff and stick to command line scripting with TCL. It's just more reliable, less prone to, well, hiccups.
So engineers might love the engine, but fight the dashboard. Are there other issues, maybe deeper ones? You mentioned logic incorrect problems. That sounds worrying.
Yes, and those are more concerning than just GUI crashes. Even AMD support acknowledges the tool can sometimes crash on really complex code, but the bigger worry is these logic incorrect issues. That's where the tool silently creates hardware that doesn't actually match your VHDL or Verilog logic. It's been reported with tricky state machines, how it shares arithmetic units, even some system Verilog things like unions.
Silently. So it compiles fine, no errors, but the chip does the wrong thing.
Potentially, yes. And the workarounds often involve turning off important optimizations, so you end up trading performance for basic correctness. That's a tough spot for any designer. It makes verification absolutely critical.
Wow. Yeah, that solid core flawed shell really hits home there. Powerful, but you have to be constantly vigilant. Okay, let's shift gears. Our next big player, Intel Quartus Prime. We call this one the high-speed integrator.
Right. Quartus Prime is designed as this really comprehensive, integrated environment, and it has deep connections to Intel's other technologies, processors, data center stuff. It covers their whole FPGA range with light, standard, and pro editions. So it scales from, networking gear up to big data center accelerators.
So if Vivado's strength is that raw, high-density compute, where does Quartus really shine? What's his special sauce?
Quartus is particularly strong in high-speed applications, especially where integration is key. Think networking infrastructure, 5G systems. It has some really good system-level tools, Platform Designer, for example.
Platform Designer.
Yeah, it helps automate connecting IP cores together, cuts down on manual wiring errors, speeds up that whole integration process. And there's Interface Planner, too, which helps with pin assignments, checks legality in real time, helps avoid mistakes that could mean re-spinning your board.
Okay, so it's strong on the integration side, high-speed stuff. How about raw performance, compile times? How does it stack up against Vivado there?
Performance-wise, it has things like multi-processor support to speed up compiles. But honestly, comparing it directly to Vivado, it's mixed. Highly dependent on your specific design, the hardware you're targeting. Some say Quartus is faster for smaller builds. Others find Vivado better for massive ones. No simple answer there.
And the user experience, does it suffer from similar issues to Vivado, or is it smoother sailing?
Well, it faces some similar criticisms. The UI, many find it less intuitive than some others, a bit of a steeper learning curve, perhaps. And that GUI freezing issue, that's a really common complaint with Quartus, too.
Freezing after compilation.
Yeah. Finishes a big compile, then the GUI just hangs. Often needs a manual kill. So again, it pushes people towards scripting for stability. But maybe a bigger issue, especially for teams, is project migration.
Moving a design from an older Quartus version to a newer one?
Exactly. It's widely reported as being really difficult, often breaking things up unexpectedly. People talk about losing serious man-hours just trying to update. It forces teams into what they call version locking.
Version locking, meaning they just refuse to update the tool. Stick with an old version because migrating is too painful.
Pretty much. Find a version that works for a project and just stay there to avoid the risk of the new version breaking the build. It's a significant hassle, especially for long-term projects.
Yeah, that sounds like a major drag on keeping tools up to date. Any other unique quirks with Quartus, things that make designers scratch their heads?
Absolutely. One that really raises eyebrows is this phenomenon called silent optimization. It's where the synthesis engine gets, well, overly aggressive.
How so?
It might decide some part of your circuit isn't needed, maybe an unconnected wire, maybe logic it thinks is redundant, and just optimize it away without telling you. No error, no warning.
Wait, it just removes part of your design.
Potentially. And this can lead to really subtle bugs. The hardware doesn't do what you intended, but the tool gave you a clean bill of health. Makes debugging a nightmare because you're chasing ghosts caused by the tool itself.
Wow. That erodes trust, doesn't it? How can you be sure the output matches your intent?
It's a huge issue. It forces incredibly thorough, sometimes painful, verification. You almost have to assume the tool might have changed something critical. And then there's the licensing, the free Elite edition. It lacks really crucial stuff like proper timing analysis, power analysis, limits its usefulness for serious learning or professional work quite a bit.
That's a critical point. You can't really validate a professional design without timing analysis. So the free version is more of a taster, really.
Okay, from these complex giants, let's turn to something different. Microchip Libero. This one seems carved out as the security and reliability specialist.
Definitely. Libero lives in a very specific niche, microchip's non-volatile flash-based FPGAs. Its whole focus is different. It prioritizes low power, rock-solid reliability, especially in extreme environments, and high security. Think aerospace, defense, medical devices, places where failure is absolutely not an option.
Flash-based FPGAs, that's different from the SRAM-based ones in AMD and Intel, right?
Yeah.
What advantages does that bring for these critical applications? It's a fundamental difference. Flash-based means the devices hold their configuration even when powered off. They boot instantly. No need for external configuration memory, no cold start delay. That's huge for systems that need to be ready immediately.
Ah, okay. Instant on. Makes sense for critical systems.
Exactly. Plus, that flash architecture gives them inherent resistance to single-event upsets, or SEUs. Those are bit flips caused by radiation, a major concern in space or high-altitude applications. Libero also provides strong, secure programming features for production. And interestingly, it relies on well-regarded third-party tools for its core tasks. Synopsys, Simplify Pro for synthesis, Siemens Model Sim for simulation, so you get mature, industry-standard engines under the hood.
Sounds very robust for its niche, but specialization often means trade-offs. What are the limitations? Where doesn't it compete?
Well, it's not trying to compete on raw logic density or sheer performance like Vivado or Quartus. It's just not built for massive parallel processing or super high-speed data crunching. And Microchip has a smaller slice of the overall FPGA market.
Meaning a smaller community, fewer online resources.
Generally, yes. A smaller ecosystem, fewer public examples or forum posts compared to the big guys. That can make learning or troubleshooting a bit more challenging if you're new to it.
Okay, powerful for its niche, but maybe a bit more isolated.
Yeah.
How about getting started? Is it user-friendly? Any quirks there?
Well, this is probably Libero's biggest quirk. The installation and licensing process is notoriously difficult, often described as a multi-step gauntlet.
A gauntlet? That doesn't sound fun.
No, it's not intuitive for how people expect software installs to work today. The license server setup is separate, manual, often tricky, especially on Linux. The main installer can even fail right at the very end, leaving behind gigs of data you have to clean up manually.
Oh, lovely.
And licenses are often tied to MAC addresses, which can be a real pain if you're using a laptop and switching between Wi-Fi and wired networks, for instance.
Yikes. So definitely not a simple download and run experience. It sounds like you almost need IT support just to get it installed.
That's often the case. It really signals an enterprise-first approach. It effectively screens out casual users, students, hobbyists. It's designed for large organizations with dedicated IT infrastructure to handle that setup complexity. It's a significant barrier if you're not in that environment.
Okay, so a specialist tool with a specialist setup process. Let's move to our final tool chain, Lattice Radiant. This one seems positioned as the low-power edge specialist, maybe a bit more approachable.
That's exactly right. Lattice Radiant targets low-power, small-footprint, cost-effective designs. Think edge computing, IoT devices, consumer electronics. Its whole philosophy is built around ease of use. Wizard-driven GUI, optimized for their small and mid-range FPGAs like the Nexus and Avant families.
Ease of use sounds like a breath of fresh air after the others. What makes it accessible and efficient?
Well, people genuinely praise it for being, quote, cute, simple, and not totally oversized, which is a stark contrast, right? The installer is way smaller, like 20 times smaller, and installs much faster, maybe 10 times faster than the big tools.
20 times smaller. That's amazing.
Yeah, it's lightweight. And that translates to faster compile times too, especially important for those fast-moving consumer markets. They claim recent releases are 25% faster for their Nexus devices. Plus, they have the Propel design environment, which helps speed up embedded system development with templates and easier IP integration.
Sounds great for its target market. So what's the catch? What are the limitations? It's obviously not trying to be Vivado.
Exactly. Its strength is its focus, which is also its limitation. Radiant is not for high-performance computing. It doesn't have the scale, the raw power for those really demanding jobs that AMD and Intel focus on. If you need huge logic counts or data center speeds, Radiant just isn't the right tool.
Makes sense. Stick to the niche. Any unique quirks with Radiant, especially around licensing or usability?
Yes, they have a pretty unique IP core licensing model. It's interesting. You get access to all the IP core source code for your design and simulation, even prototyping on hardware without buying a license up front.
Really? Free access to all IP?
For evaluation, yes. But here's the twist. If you don't buy the license for the final product, the tool inserts a hardware timer into your bitstream. Your design will work, but it'll stop after somewhere between 30 minutes and maybe 4 hours.
Okay, so a timed demo baked into the hardware itself. Clever?
It is clever. It lets you fully evaluate everything for free, prototype extensively, but you absolutely need to buy the license to ship a real product. Also, Linux support is officially only for a couple of distributions like Red Hat and Ubuntu. Users on other distros like Arch report GUI problems sometimes, often because of bundled libraries. They end up using the command line tool, Radiant ECA, instead. And, if we connect this to the bigger picture, Radiant's focus on these smaller, less complex FPGAs, it's actually helped foster something important, viable open source toolchains.
Ah, right, like Yossi's and XPNR.
Exactly. Because the lattice architectures are, relatively speaking, more manageable, the open source community has actually managed to build good working toolchains for them. That gives users a real alternative to the official vendor tools, a level of freedom you just don't see yet in the high-end AMD Intel space.
Okay, so we've walked through 4 very different tool chains. Vivado the Titan, Quartus the integrator, Libero the reliable specialist, and Radiant the accessible edge tool. What's the big takeaway here?
I think the biggest takeaway is just how clear it is. There's no single best tool. It's always about finding the most suitable tool for your specific project needs, your priorities, and maybe even your tolerance for frustration.
Right. And even something seemingly simple like compile speed isn't straightforward. You mentioned Vivado versus Quartus there.
Yeah, exactly. Simple benchmarks might show Quartus faster on small stuff, but Vivado, with its focus on huge designs and its incremental compile features, can actually be much faster for really complex projects where you're only changing small parts. Quartus might struggle more with those massive rebuilds. Vivado's initial startup, though, can feel slow for quick little builds. Different strengths.
And it seems like the frustrations people feel with these big, sometimes buggy, proprietary tools are a real driving force behind the open source efforts, especially for Lattice.
Definitely. But as we said, the sheer complexity of the high-end AMD and Intel chips makes creating open source equivalents incredibly difficult. It's a massive undertaking. So for now, users needing that top-tier performance are pretty much tied to the vendor tools, warts and all. It also highlights these totally different philosophies on licensing, doesn't it?
Yeah, that was striking. Vivado free but limited devices. Quartus.free but limited features, missing key analysis tools. Libero.free, but good luck installing it if you're not a large enterprise. And Lattice free, to try everything but with that timed hardware limitation.
Each approach tells you something about how the vendor sees its users and the market, who they're trying to attract, and how they expect you to pay.
So it really dictates the entry point for innovation depending on who you are.
Which brings us to the crucial question.
Yeah.
How do you, the listener, choose the right tool? It really comes down to mapping your product needs to these tool strengths. So, rough guides might look like this. If you're a student or hobbyist, Lattice Radiant is probably your best starting point. Easy GUI, small install, fast compiles, that free IP prototyping is great. Maybe Vivado ML Standard or Quartus Lite as secondary options.
Okay. What about researchers?
Academic researchers needing serious horsepower or advanced features. Probably Vivado, either ML Standard or the full enterprise version, especially with Vetus HLS for complex algorithms, AML work. Quartus Prime could be a secondary choice.
High-performance computing, AI data centers.
That's Vivado territory. AMD's whole focus is there. High-density chips, Vitus for acceleration, Quartus Prime is the runner-up.
High-speed networking, 5G.
That's often Quartus Prime's sweet spot. Intel's integration story with transceivers, processors, platform designer really helps there. Vivado is secondary.
Low-power IoT, edge devices.
Lattice Radiant is the specialist there. Fast iteration, low power focus. Microchip Libero could be an option too, especially if reliability is paramount.
And for that ultimate security, reliability, maybe radiation tolerance.
Microchip Libero SOS. That flash architecture, the security focus, it's built for mission critical. Maybe some secure AMD devices using Vivado as a secondary consideration, depending on exact needs.
Okay, those are great guidelines. But what if you're already stuck with a tool? Or your company mandates one? Are there ways to just cope? Survival strategies.
Yes, definitely survival strategies. If you're deep in Vivado, the common advice is learn TCL scripting. Avoid the GUI for complex critical flows where stability matters most. Rely on scripts.
Okay, scripted is for Vivado. Quartus.
For Quartus, that version locking strategy is key. Find a version that works reliably for your project and stick with it. Avoid unnecessary updates mid-project if you can, unless there's a critical bug fix you absolutely need. Document everything.
Makes sense. Libero.
Libero. Well, dedicate a machine if you can. Maybe get IT involved if possible. Budget extra time for installation and license setup. Be prepared for manual troubleshooting. Patience is definitely a virtue.
And Radiant.
With Radiant, it's less about fighting the tool and more about respecting its boundaries. Understand its architectural limits. Don't try to make it do massive HPC tasks it wasn't designed for. Embrace its strengths in the low-power, mid-range space. And looking forward, what's really fascinating is how this landscape is changing. The user frustration is palpable, and it's fueling things like the F4PGA open source initiative.
Right, trying to build vendor-neutral tools.
Exactly. And at the same time, you have HLS gaining traction, potentially bringing more software folks into the fold. These trends suggest maybe, just maybe, the future isn't just about picking one giant vendor suite. Maybe it's more about mixing and matching the best tools for the job, whether they're proprietary or open source, building a more flexible, stable ecosystem.
So this deep dive really hammers home that picking an FPGA toolchain isn't just a technical choice, it's a strategic one. Each tool has its own personality, its own power, and its own set of quirks you need to learn to live with.
Which leaves us with a final thought to maybe mull over. We see the clear frustrations with today's proprietary tools, and we see the promise, the growing strength of open source alternatives, at least for some FPGAs. So the question is, will open source eventually liberate designers from these vendor-specific quirks and lock-ins? Or is the sheer complexity of those high-end chips always going to demand these massive, bespoke proprietary solutions? Something to definitely ponder as you tackle your next design challenge.